Think about this moment right now. You're aware of it happening, this present instant, this now. But what is now exactly? Where does it exist? And more strangely still, could it exist at all without the space around you, without the room you're in, without the physical universe itself? For most of human history, these questions would have seemed absurd. Time was time. Space was space. They were separate things, as different from each other as water is from stone. Time flowed forward like a river, universal and absolute, the same for everyone everywhere. Space was the stage on which events unfolded, the container for all things. They seemed as independent as two concepts could be. But then, in the early years of the 20th century, everything changed. Einstein's theories of relativity didn't just modify our understanding of space and time. They shattered the very idea that these two things could be separated at all. Space and time, it turned out, are woven together into a single fabric called spacetime. And this discovery opened up one of the most profound questions we can ask about reality itself. Can time exist without space? Is time an independent entity that could, in principle, exist on its own? Or are time and space so fundamentally intertwined that one cannot exist without the other? Tonight, we're going to explore this question from multiple angles. We'll journey through the physics of relativity, where space and time merge into an inseparable unity. We'll peer into the earliest moments of the universe, where the very concept of before might become meaningless. We'll grapple with quantum mechanics, which treats time in a completely different way and creates deep tensions with relativity. We'll encounter theories suggesting time itself might not be fundamental at all, but something that emerges from deeper, timeless physics. And we'll consider how all of this relates to our own lived experience, the flow of moments that makes up our conscious lives. This is a journey into some of the deepest mysteries physics and philosophy have to offer. The answers aren't simple, and in many cases, we don't have answers at all. But the questions themselves are beautiful, and thinking about them changes how we understand both the universe and our place within it. So settle in, get comfortable, and let's explore together whether time could exist without space, or whether these two fundamental aspects of reality are, at the deepest level, one and the same. To understand whether time can exist without space, we first need to understand how physicists came to realize these two things are connected in the first place. And that story begins in the world that Isaac Newton built. In Newton's universe, time and space had completely separate identities. Time was absolute. It flowed uniformly, everywhere, always at the same rate. A second was a second. Whether you measured it on Earth or Jupiter, whether you were standing still or moving, Newton imagined time as a kind of cosmic clock, ticking away independent of anything that happened within it. Meanwhile, space was the three-dimensional arena where things existed and moved. It too was absolute, a fixed stage that wasn't affected by the objects it contained. You could measure distances, positions, and velocities against this unchanging background. This view was enormously successful. Newtonian physics could predict the motions of planets, explain the behavior of falling objects, and describe the mechanical world with stunning precision. For more than 2 centuries, it was the foundation of all physics. Time did its thing, space did its thing, and never the twain shall meet. But there were cracks in this foundation, and they showed up in the study of light and electromagnetism. In the middle of the 19th century, James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetism. His equations described light as a wave, an oscillation in electromagnetic fields, and these equations predicted a specific speed for light, a number that fell out of the mathematics itself, approximately 300,000 kilometers per second. Here's what was strange about that. The speed didn't depend on who was measuring it, or how they were moving. In Newtonian physics, speeds are relative. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the ground would measure the ball moving at 70 kilometers per hour, the sum of the two speeds. But Maxwell's equations suggested light didn't work this way. This seemed impossible. Physicists tried to explain it by proposing that light traveled through a medium called the luminiferous ether, a substance that filled all of space and provided a fixed reference frame. But experiments, most famously the Michelson-Morley experiment in the late 1880s, found no evidence for any such ether. Light's speed was constant, and no one knew why. Enter Albert Einstein in 1905. At age 26, working as a patent clerk in Switzerland, Einstein published a paper that would change physics forever. The paper was called On the Electrodynamics of Moving Bodies, and it introduced what we now call special relativity. Einstein's insight was radical in its simplicity. What if we just accept that the speed of light is the same for all observers? What if that's a fundamental law of nature? Not something that needs explaining away. But accepting this required abandoning Newton's absolute time and space. If the speed of light is constant for everyone, then something else has to give. And what gives is the independence of space and time. Here's a way to think about it. Imagine you're on a train platform and a train passes by at high speed. Someone on the train shines a flashlight forward. You both measure the speed of that light. According to Newton, you should measure different speeds because you're moving relative to each other. But according to Einstein, you both measure exactly the same speed. How is that possible? The answer is that time itself must pass at different rates for the two of you. From your perspective on the platform, time is running more slowly on the train. The person on the train ages more slowly, their clocks tick more slowly. Even their thoughts unfold more slowly, though they don't notice it themselves because everything is slowed down equally. Meanwhile, from the perspective of the person on the train, it's your time that's slowed down. Each of you sees the other's time dilated, and it's not just time. Distances change too. The train, from your perspective on the platform, is actually slightly shorter than it would be if it were standing still. This is called length contraction. Space and time both have to be flexible, malleable, relative to the observer's motion, in order for the speed of light to be constant for everyone. These aren't just theoretical oddities. They've been confirmed by countless experiments. Atomic clocks flown on airplanes tick at different rates than identical clocks left on the ground, exactly as relativity predicts. Particles created in accelerators live longer when they're moving at high speeds because time is literally passing more slowly for them. GPS satellites have to account for relativistic time dilation, or they'd quickly give incorrect positions. Relativity isn't speculation, it's reality. But Einstein's special relativity, as revolutionary as it was, only dealt with constant velocities. It didn't include gravity. And when Einstein spent the next decade figuring out how to incorporate gravity into his new framework, he discovered something even more profound. Before we get there, though, we need to talk about Hermann Minkowski. Minkowski had been Einstein's mathematics professor years earlier, and he immediately recognized something that Einstein himself initially missed. In 1908, 3 years after Einstein's special relativity paper, Minkowski gave a famous lecture in which he presented a geometric interpretation of relativity. Minkowski showed that space and time aren't just related, they're fundamentally unified. They're different aspects of a single four-dimensional structure, which he called spacetime. In Minkowski's formulation, an event doesn't happen at a certain time and a certain place. It happens at a certain point in spacetime, specified by 4 coordinates, 3 for space and 1 for time. The famous quote from Minkowski's lecture captures the revolutionary nature of this idea. Henceforth, space by itself, and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Think about what this means. In the old Newtonian view, you could meaningfully separate time from space. You could ask, "What's happening everywhere right now?" and get a definite answer. There was a universal present moment, a single now that extended across all of space. But in Minkowski space-time, there's no such thing. Whether two events are simultaneous depends on your frame of reference, on how you're moving. Your now and my now, if we're in relative motion, are different slices through space-time. Imagine space-time as a loaf of bread. The Newtonian view is that there's one correct way to slice the loaf, perpendicular cuts that represent universal moments of time. But in Minkowski space-time, there are infinitely many ways to slice the loaf, and each one is equally valid. Different observers, moving at different speeds, slice space-time differently. They disagree about which events are simultaneous, about the order in which some events occur, about measurements of time and distance. Yet, despite these disagreements, there's something that everyone does agree on. While space measurements and time measurements vary from observer to observer, there's a combination of space and time, a kind of space-time distance, that's the same for everyone. Physicists call this the space-time interval. And it's the invariant reality underlying all the relative measurements. Einstein initially resisted Minkowski's geometric framework. He thought it was unnecessary mathematical abstraction. But when he turned to the problem of gravity, he changed his mind completely. The language of spacetime, the mathematics of four-dimensional geometry, proved essential to his greatest achievement. General Relativity, published in 1915, extended special relativity to include gravity, and Einstein's insight here was even more radical than before. He proposed that gravity isn't a force at all, at least not in the traditional sense. Instead, gravity is the curvature of space-time itself. Massive objects, like stars and planets, warp the fabric of space-time around them. If you then roll a marble across the sheet, it will curve toward the bowling ball, not because the ball is exerting a force on it, but because it's following the curved geometry of the sheet. In the same way, Earth orbits the Sun not because the Sun reaches out and pulls on it, but because the Sun curves space-time, and Earth is simply following the straightest possible path through that curved space-time. What we experience as the force of gravity is really just the curvature of space-time telling objects how to move. But here's the crucial point for our question about time and space. In general relativity, it's not just space that curves. Space-time curves. Time is bent along with space. This means that time passes at different rates in different gravitational fields. The stronger the gravity, the slower time flows. This has been measured. Clocks at different altitudes tick at different rates. A clock at sea level runs slightly slower than one on a mountaintop because it's deeper in Earth's gravitational field. The effect is tiny, just fractions of a second over a lifetime, but it's real and measurable. GPS satellites have to account for this or the system wouldn't work. Near extremely massive objects, the effect becomes dramatic. Near a black hole, where gravity is incredibly strong, time slows down enormously. An observer watching someone fall toward a black hole would see them slow down, their motion becoming slower and slower, asymptotically approaching but never quite reaching the event horizon. Meanwhile, from the perspective of the person falling, their own time seems normal. General relativity revealed that space-time is not a fixed stage. It's a dynamic, flexible entity that responds to the presence of mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. It's a beautiful, self-consistent loop, and crucially, in this framework, space and time are inseparable. You can't have curvature of space without also having curvature of time. They're aspects of the same geometric structure. The very mathematics of general relativity treats them on equal footing, mixing them together in the equations. Now, there's a subtlety here worth mentioning. Even though general relativity unifies space and time into spacetime, it doesn't make them identical. Time still has special properties that space doesn't have. For one thing, we can move freely through space in any direction, but we can only move forward in time, at least as far as we know. Time has an arrow, a direction, while space doesn't, and mathematically, the time dimension enters the equations with a different sign than the space dimensions, a minus sign in what physicists call the metric. This minus sign is what distinguishes time from space mathematically. So time and space aren't completely the same, but they are inextricably linked. In general relativity, you cannot have one without the other. The very concept of space-time curvature requires both dimensions. A universe with space but no time, or time but no space, isn't just unlikely. It's geometrically incoherent within this framework. Think about what this means for our original question. In the Newtonian world, you could imagine time existing independently, ticking away even in the absence of space. But in Einstein's world, that doesn't make sense. Time is a dimension of space-time, bound to the spatial dimensions by the geometry that describes gravity and the structure of the universe. This was the first great revolution in our understanding of time's relationship to space. But it wouldn't be the last, because when physicists turned their attention to the very beginning of the universe, to the Big Bang itself, they encountered an even stranger possibility: that time and space might not just be connected, but that time itself might have a beginning, coming into existence along with space in a moment of creation where the very question, what came before, becomes meaningless. If time and space are unified, as relativity tells us, then what happens at the beginning of the universe takes on a profound significance. Because if the universe had a beginning, then perhaps time itself had a beginning. And if time began, then asking, what came before the Big Bang, might be like asking, what's north of the North Pole? This possibility has fascinated physicists and philosophers for decades. Let's explore how we got here and what it might mean. The story begins with the discovery that the universe is expanding. In the 1920s, astronomer Edwin Hubble made observations that would transform our understanding of the cosmos. He found that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe isn't static, it's growing, expanding, getting bigger with every passing moment. This discovery had a profound implication. If the universe is expanding now, then it must have been smaller in the past. Run the clock backward, and the universe gets denser and denser, hotter and hotter. All the matter and energy that now fills billions of light years of space was once compressed into an incredibly tiny, incredibly dense state. Georges Lemaitre, a Belgian priest and physicist, was actually the first to propose this idea, even before Hubble's observations. Lemaitre called it the primeval atom, or cosmic egg. We now call it the Big Bang, though that term was actually coined by Fred Hoyle, who was skeptical of the idea and meant it somewhat derisively. The Big Bang theory suggests that the universe began approximately 13.8 billion years ago in an incredibly hot, dense state and has been expanding and cooling ever since. The evidence for this is overwhelming. We can see the afterglow of the Big Bang in the cosmic microwave background radiation, a faint glow of photons that has been traveling through space for nearly 14 billion years. We can measure the abundances of light elements like hydrogen and helium, which match the predictions of Big Bang nucleosynthesis. We can observe the large-scale structure of galaxies, which formed from tiny quantum fluctuations in the early universe. But here's where things get strange. If you follow the mathematics of general relativity backward in time toward the beginning, you encounter a problem. The density and temperature increase without limit. All of space, and all the matter and energy it contains, seems to converge on a single point of infinite density and infinite curvature. This is called a singularity. At a singularity, the equations of physics break down. Densities become infinite. Temperatures become infinite. The curvature of space-time becomes infinite. You can't calculate what happens there because dividing by zero or working with infinities doesn't give you meaningful answers. General relativity, which works so beautifully to describe the universe on large scales and at reasonable densities, simply fails at the conditions of the Big Bang singularity. This led Stephen Hawking and Roger Penrose, in the 1960s, to prove a set of theorems showing that singularities are generic in general relativity. Under reasonable assumptions about the nature of matter and energy, you can't avoid them. If you have an expanding universe like ours, then running the equations backward inevitably leads to a singularity. The universe, according to general relativity, cannot have had a smooth, ordinary beginning. Something more extreme, something beyond the reach of the theory, must have occurred. Now, most physicists don't believe the singularity is a physical reality. Rather, it's a signal that general relativity is incomplete. At the incredibly high energies and tiny scales near the Big Bang, quantum effects become important. We need a theory of quantum gravity, a framework that successfully merges general relativity with quantum mechanics, and we don't fully have that yet. But even without a complete theory of quantum gravity, physicists have proposed ideas about what might have happened at the beginning, and one of the most influential and fascinating proposals came from Stephen Hawking and James Hartle. While speculative and still debated among cosmologists, their no-boundary proposal offers a radical possibility that the question itself is meaningless, not because we don't know the answer, but because time itself began with the Big Bang. There is no before. The universe is finite in time, but has no boundary, no edge, no beginning in the conventional sense. Hawking liked to use an analogy to explain this. Imagine you're traveling south on Earth's surface. You can go south from New York to Miami, from Miami to Quito, from Quito toward the South Pole. But once you reach the South Pole, the concept of south loses its meaning. You can't go any further south because you're already at the southernmost point. Asking what's south of the South Pole doesn't make sense. There's nothing wrong with the question grammatically, but it doesn't correspond to any physical reality. In the same way, Hawking and Hartle proposed that time is like a direction on a curved surface. You can go backward in time, earlier and earlier, approaching the Big Bang, but once you reach the Big Bang, the concept of earlier loses meaning. There is no before the Big Bang because time itself didn't exist before then. The Big Bang is the boundary of time, but like the South Pole, it's a smooth point, not an edge or a wall. How does this work mathematically? The key is something called imaginary time. This is where things get rather abstract, but stay with me. In normal, everyday physics, time is a real number. It increases from the past to the future, and we use real numbers to measure it. Seconds, minutes, years. But in quantum mechanics and in certain mathematical frameworks for dealing with curved spacetime, physicists sometimes use imaginary numbers for time. These are numbers that involve the square root of -1, represented by the letter I. Now, imaginary numbers might sound like pure fiction, but they're actually extremely useful in mathematics and physics. They're not imaginary in the sense of being made up or unreal. They're a different type of number with their own well-defined properties. In the Hartle-Hawking proposal, as you go back toward the Big Bang, time gradually changes character. It transitions from being a real number, the kind we experience, to being an imaginary number. And when time is imaginary, the mathematics of space-time changes in a crucial way. The distinction between time and space disappears. Think of it this way. In normal space-time, time is different from space. It's the dimension we can't control, the one that only goes forward. But in Euclidean space-time, which is what you get when you use imaginary time, all four dimensions are on equal footing. Time becomes just another spatial dimension. There's no arrow, no preferred direction, no distinction between past and future. So in the Hartley-Hawking model, the very early universe exists in this Euclidean state where time is spatial. There's no boundary because there's no edge to space. The universe is finite in extent but boundaryless, like the surface of a sphere. Then, as the universe expands and cools, time transitions from imaginary to real. It becomes the temporal dimension we experience, with its arrow pointing from past to future. The transition is smooth and continuous. There's no dramatic moment where time turns on. Rather, time emerges gradually from a state where it didn't exist as a distinct dimension. Hawking put it beautifully in a lecture. Asking what came before the Big Bang is meaningless, according to the no-boundary proposal, because there is no notion of time available to refer to. It would be like asking what lies south of the South Pole. Now, it's important to understand that the Hartley-Hawking no-boundary proposal is one hypothesis among several competing ideas about the universe's origin. It makes certain predictions that have been checked against observations of the cosmic microwave background, and so far, the agreement is good. The pattern of temperature fluctuations we see in the CMB matches what the no-boundary proposal predicts should emerge from quantum fluctuations in the early universe. But there are other proposals too. Some physicists argue that the universe might have existed in some form before the Big Bang, perhaps in a contracting phase that then bounced into expansion. Others suggest the universe might have emerged from a quantum fluctuation, a spontaneous creation event allowed by the probabilistic nature of quantum mechanics. Still others work with string theory frameworks that propose extra dimensions or multiple universes. The question of what happened at the universe's origin remains open, with various theoretical approaches being explored and debated. The point isn't that Hartley-Hawking is definitely correct. The point is that when we take seriously the unity of space and time, when we follow the implications of relativity and quantum mechanics back to the origin of the universe, we're forced to confront the possibility that time itself is not eternal. Time might have a beginning, and if it does, then the concept of before the Big Bang is incoherent. This has profound philosophical implications. For centuries, humans have asked, why is there something rather than nothing? The Big Bang seemed to push this question back to a first moment. But if time itself began with the Big Bang, these questions don't work. There was no before, no moment when the universe didn't exist but could have been created. The universe, in some sense, is all there is, a self-contained space-time structure with no external beginning or cause. Stephen Hawking emphasized this point in a lecture he gave at the Vatican in 2016, 18 months before his death. Events before the Big Bang are simply not defined because there's no way one could measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang. Think about what a strange situation this is. We're used to asking why about everything. Why did this happen? What came before that? What caused it? But at the origin of the universe, if time itself began there, the chain of causation has no prior link. It's not that we don't know what came before. It's that before doesn't exist. The universe doesn't have a cause in time because time is part of the universe. Now, you might wonder, doesn't this make space-time even more inseparable? If time and space both came into existence together at the Big Bang, doesn't that prove they can't exist independently? In one sense, yes. The Big Bang picture suggests that our space-time, the four-dimensional structure we inhabit, is a unified whole that began as a complete package. You don't have time existing first and then space emerging later, or vice versa. They come into being together as aspects of a single geometric structure. But there's a nuance worth considering. The transition from Euclidean spacetime with imaginary time to Lorentzian spacetime with real time suggests that the character of time can change. In the Euclidean regime, time is spatial. In the Lorentzian regime, it's temporal. This hints that the relationship between time and space might be more subtle than it first appears. Perhaps under extreme conditions, the distinction we make between them can blur or even disappear. We'll return to this idea later when we explore theories where time is emergent. Because quantum mechanics, our best theory of the microscopic world, treats time in a completely different way than general relativity does. And this difference creates one of the deepest puzzles in all of physics. We've seen how relativity unifies space and time into spacetime, making them inseparable aspects of a curved geometric structure. But there's another fundamental theory of physics, equally successful and equally important: quantum mechanics. And quantum mechanics has a very different relationship with time, one that creates profound tensions when we try to combine it with relativity. In quantum mechanics, time occupies a special, privileged role that sets it apart from space and from everything else in the theory. And this difference is at the heart of what physicists call the problem of time. Let's start with the basics. Quantum mechanics is the physics of the very small, of atoms and electrons and photons. It describes a probabilistic world where particles don't have definite positions until you measure them, where the same particle can be in multiple states at once, where effects can be instantaneous across arbitrary distances. It's strange, counterintuitive, and thoroughly verified by countless experiments. The central equation of quantum mechanics is the Schrödinger equation. This equation describes how quantum states evolve. If you know the state of a quantum system at one time, the Schrödinger equation tells you what the state will be at any future time. Here's the key thing about the Schrödinger equation. Time appears in it as a parameter, not as an observable. What does that mean? In quantum mechanics, observable quantities are represented by operators. There's a position operator, which you use to measure where a particle is. There's a momentum operator for measuring how fast and in what direction it's moving. There's an energy operator, a spin operator, operators for all the properties you can measure. These operators act on the quantum state, and when you make a measurement, you get one of the operator's eigenvalues as your result. But there's no time operator. Time isn't something you measure in quantum mechanics. Instead, time is a background parameter that labels when measurements happen. You measure the position at time t, or the energy at time t, but you don't measure time itself. Time sits outside the quantum system, an external classical variable against which the quantum evolution unfolds. This might not sound like a big deal, but it has important consequences. For one thing, it means time is absolute in quantum mechanics, unlike in relativity, where different observers disagree about time measurements. In standard quantum mechanics, there's a universal time that everyone agrees on. Events happen at definite times, and the time ordering of events is the same for all observers. This is already in tension with special relativity, where simultaneity is relative. But physicists know how to handle that tension. There's a relativistic version of quantum mechanics called quantum field theory that respects the principles of special relativity. It's more complicated than non-relativistic quantum mechanics, but it works. In fact, it works spectacularly well. The standard model of particle physics is a quantum field theory, and it's one of the most precisely tested theories in all of science. But when you try to combine quantum mechanics with general relativity, with the curved, dynamic spacetime of gravity, the problem of time becomes severe. In general relativity, as we've discussed, time is part of spacetime, a dimension that's on somewhat equal footing with space. The geometry of spacetime is dynamic, changing and evolving according to Einstein's field equations. Time is woven into this geometry. In quantum mechanics, time is external and absolute, a background parameter. These two descriptions are fundamentally incompatible. The tension becomes acute when physicists try to quantize gravity to create a quantum theory of space-time itself. The natural starting point is an equation called the Wheeler-DeWitt equation, named after John Wheeler and Bryce DeWitt, who developed it in the 1960s. The Wheeler-DeWitt equation is what you get when you try to apply the standard methods of quantum mechanics to the geometry of space-time. It's an equation that describes quantum states of the universe, wave functions that encode probabilities for different space-time geometries. But here's the shocking thing. The Wheeler-DeWitt equation has no time in it at all. It's a timeless equation. The wave function of the universe doesn't evolve in time. It just is. At first, this seems disastrous. How can you have quantum mechanics without evolution in time? The whole point of the Schrödinger equation is that it tells you how states change over time. But the Wheeler-DeWitt equation doesn't do that. It's more like an equation of constraint, a condition that the quantum state must satisfy, but it doesn't say how that state changes. This is the problem of time in its starkest form. When you try to create a quantum theory of gravity, of space-time itself, time seems to disappear. The fundamental description is timeless. Now, this doesn't mean that time doesn't exist or that it's purely illusory. What it suggests is that time, at the most fundamental level, might not be a basic ingredient of reality. Instead, time might be something that emerges, something that appears when you look at the universe in a certain way or at a certain scale, even though the underlying description is timeless. Think of it like this. When you look at a still photograph, there's no time in the photograph itself. It's a frozen moment. But if you have a whole series of photographs, a film strip, you can create the illusion of motion and change by flipping through them. The time you experience when watching the movie emerges from the sequence of timeless images. In a similar way, the time we experience might emerge from a fundamentally timeless quantum description of the universe. The Wheeler-DeWitt equation gives you the whole history of the universe at once, like a complete film strip. But when you're inside that history, when you're one of the frames, you experience time flowing. But how does this work in detail? How do you get time and the experience of time flowing from a timeless theory? This is an area of active research, and there are several proposals. One is called the Page-Wouters mechanism, after the physicists Don Page and William Wouters, who proposed it in 1983. The Page-Wouters idea is clever. It suggests that time emerges from correlations between different parts of the universe. Imagine the universe split into two pieces. One piece acts as a clock, and the other piece is the system you're interested in. Even though the total quantum state is timeless, when you look at just the system part, conditioned on the state of the clock, you see evolution that looks like normal quantum mechanics unfolding in time. In other words, time is relational. It's not an absolute background against which things happen. Instead, time is the correlation between a physical clock and other physical processes. Different choices of clock give you different notions of time. This idea has been developed and refined in recent years. Researchers have shown that if you take a quantum system and entangle it with another system that acts as a clock, with time evolution given by the Schrödinger equation, even though the total state is described by a timeless Wheeler-DeWitt equation. While this approach has gained attention and shown theoretical promise, It remains a proposal still being developed and debated among physicists, with ongoing research exploring its implications and potential limitations. Quantum entanglement, that strange connection where two particles remain linked no matter how far apart they are, might be the key to understanding time itself. Time might be a consequence of entanglement, an emergent phenomenon that arises when quantum systems become correlated with each other. Alessandro Copo, a physicist who has worked on this, puts it beautifully. The correlation between the clock and the system creates the emergence of time, a fundamental ingredient in our lives. If this is right, then in a universe with only one particle, with nothing to act as a clock and nothing to correlate with, time wouldn't exist. Time requires multiplicity, interaction, correlation. It's fundamentally a relational concept. Now, there's another aspect of the problem of time worth mentioning: the conflict between time symmetry and the arrow of time. The fundamental equations of physics, both classical and quantum, are time symmetric. If you take a solution to these equations and run it backward in time, you get another valid solution. Nothing in the basic laws distinguishes past from future. There's no arrow built into the equations, yet we experience a very definite arrow of time. The past is different from the future. We remember the past but not the future. Causes precede effects. Entropy increases. Time has a direction, an asymmetry, even though the fundamental laws don't. In quantum mechanics, this tension is particularly acute during measurement. The Schrödinger equation, which governs how quantum states evolve, is perfectly time symmetric. If you reverse time, a quantum state that was evolving forward will evolve backward in the same way. But when you make a measurement, something different happens. The quantum state collapses from a superposition of possibilities into a definite outcome. This collapse is irreversible and asymmetric in time. It picks out a direction. Where does this asymmetry come from? How does the arrow of time emerge from time-symmetric laws? This is deeply connected to the second law of thermodynamics, which states that entropy, roughly speaking the disorder or randomness of a system, always increases. But that's a story we'll explore in more detail when we talk about emergent time. For now, the key point is that quantum mechanics and general relativity have fundamentally different relationships with time. Quantum mechanics treats time as an external parameter, absolute and universal. General relativity treats time as part of spacetime, relative and dynamic. And when you try to quantize spacetime, time seems to disappear entirely from the fundamental description. This suggests something profound. Our everyday notion of time, the flow of moments from past to future, might not be fundamental. It might be an approximate, emergent property that appears only at certain scales or in certain limits. The deep reality might be timeless, or at least, time might work in ways we don't yet fully understand. But there's another possibility, one that some physicists have taken seriously. Maybe time and space aren't so inseparable after all, at least not at the most fundamental level. Maybe under extreme conditions, like those in the very early universe or near black holes, space and time can behave independently, or one can dominate while the other fades away. This brings us to theories of emergent time, where physicists propose that time, as we know it, arises from something deeper. These theories suggest that asking whether time can exist without space might be the wrong question. The right question might be, do either time or space exist fundamentally, or are they both emergent from a more basic, perhaps timeless, reality? We've explored how relativity binds time to space and how quantum gravity makes time disappear from the fundamental equations. Now we turn to a radical idea that some physicists take seriously. That time, as we experience it, doesn't exist at the most fundamental level. Instead, time emerges from a deeper, timeless reality, much like temperature emerges from the motion of atoms or wetness emerges from the behavior of water molecules. This idea might sound strange, but it's grounded in serious physics and mathematics. And one of its most eloquent advocates is Carlo Rovelli, an Italian theoretical physicist who's one of the founders of a theory called loop quantum gravity. Loop quantum gravity is an attempt to create a quantum theory of spacetime. Unlike string theory, which adds extra dimensions and exotic particles, loop quantum gravity works with the ingredients we already have: space, time, and gravity. It takes general relativity seriously and tries to quantize it directly. In loop quantum gravity, space itself is quantized. Just as energy comes in discrete packets called quanta, space in this theory comes in discrete chunks. At the smallest scale, the Planck scale, about 10 to the minus 35 meters, space has a granular structure. It's woven from discrete loops and nodes, forming what physicists call a spin network. These loops aren't embedded in space. They are space. There's no background geometry. The spin network is the geometry. And crucially, this geometry doesn't evolve in time because time, in loop quantum gravity, doesn't exist at the fundamental level. Rovelli has been very clear about this. In the fundamental description, there is no time variable. The universe is described by quantum states of geometry, spin networks, but these states don't change in time because there's no time for them to change in. The theory is timeless, just like the Wheeler-DeWitt equation. So where does time come from? How do we get from this timeless description to the flowing time we experience? Rovelli's answer involves thermodynamics and entropy, what he calls the thermal time hypothesis. He argues that time emerges when we have incomplete information about a system, when we describe it statistically rather than exactly. Here's the idea. If you knew the exact quantum state of every particle in the universe, down to the last detail, you wouldn't need time. You could see the entire history of the universe laid out like a completed sculpture, all moments existing at once. There would be no preferred variable that acts as time, no sense of past and future, just correlations between different parts of this complete configuration. But we don't have complete information. We can't track every particle, every degree of freedom. Instead, we use statistical descriptions, averages, macroscopic variables. We talk about temperature instead of the velocities of individual atoms. We talk about pressure instead of the momentum transfers of individual collisions. And when you use these statistical descriptions, something remarkable happens. A preferred variable emerges that acts like time. This variable is related to entropy, to the number of microscopic configurations compatible with your macroscopic description. And processes naturally tend to flow in the direction of increasing entropy, creating an arrow of time. Rovelli calls this thermal time. It's the time that emerges from thermodynamics, from our coarse-grained view of reality. It's not fundamental, but it's what we experience. The flow of time, in this view, is intimately connected to our ignorance of the microscopic details of the universe. Think about what this means. The second law of thermodynamics, which says entropy increases, is giving us the arrow of time. The reason time flows from past to future, the reason we remember yesterday, but not tomorrow, is because we're large, macroscopic beings with limited information about the microscopic quantum state. If we were somehow able to track every quantum degree of freedom, time would lose its meaning. It would dissolve into a timeless network of correlations. In Rovelli's own words, as long as we have a complete description of a system, all the variables of the system are on the same footing. None of them act as a time variable. But as soon as we describe the system by means of averages of many variables, we have a preferred variable that functions like common time, a time along which heat dissipates, the time of our everyday experience. This is a profound inversion of how we usually think. We tend to assume time is fundamental and entropy is a consequence. But Rovelli is suggesting it's the other way around. Entropy, or more precisely, our incomplete knowledge that makes entropy useful, gives rise to time. Now, loop quantum gravity isn't the only theory proposing emergent time. There are other approaches with similar conclusions. One comes from a physicist named Petr Hojava, who proposed a theory of quantum gravity that takes a different approach. Hojava gravity suggests that at very high energies, like those in the very early universe, time and space actually separate. They're not unified into space-time in the conventional sense. Time becomes independent again, as it was in Newton's framework. In Hojava's theory, space is quantized at short distances, but time flows continuously. At low energies, the energies we experience in everyday life, but at high energies, near the Planck scale, they split apart. This solves certain mathematical problems that plague other quantum gravity theories. In particular, it tames infinities that usually appear and makes the theory mathematically well-behaved. The theory has generated excitement because it makes predictions that can potentially be tested. For instance, it might explain why galaxies seem to contain more mass than we can see, usually attributed to dark matter, as an effect of gravity behaving differently at large scales. Whether Hojava gravity is correct remains an open question, but it represents another way of thinking about the relationship between time and space. Perhaps they're unified only at certain energy scales, only in certain regimes, while at the most fundamental level, they have separate identities. Another perspective comes from studying black holes and information theory. Black holes have taught us that gravity, thermodynamics, and quantum mechanics are deeply interconnected. A black hole has entropy, proportional to the area of its event horizon. It has a temperature, called the Hawking temperature. These aren't metaphors. They're physical properties that emerge from the quantum nature of space-time near black holes. Some physicists, following insights from string theory and holography, have proposed that space-time itself might be emergent from quantum entanglement. In this view, the geometry of space and time isn't fundamental. Instead, what's fundamental is information, quantum information encoded in entangled quantum states. Space-time emerges from the pattern of entanglement, much like a hologram emerges from an interference pattern. If this is true, then both space and time are emergent, arising from something more basic that doesn't have spatial or temporal character. The question, can time exist without space, becomes less meaningful because neither exists fundamentally. They're both approximate, macroscopic descriptions of a deeper quantum informational structure. Mark van Ramsdonk, a physicist who has worked on these ideas, puts it this way: the connectivity of space, the fact that distant points are connected by a continuous geometry, is a reflection of quantum entanglement. Break the entanglement, and space-time falls apart. These are speculative ideas, still being developed and debated, but they share a common theme. Time might not be as fundamental as we think. It might be emergent, appearing only when we look at the universe in certain ways or at certain scales. Now, you might wonder, if time is emergent, does that mean it's not real? That it's somehow an illusion? That's not quite the right way to think about it. Emergent doesn't mean illusory. Temperature is emergent. It's the average kinetic energy of molecules. But that doesn't make temperature less real or less useful. A table is emergent. It's a collection of atoms held together by electromagnetic forces, but that doesn't mean you can walk through it. In the same way, emergent time is still real for us. It's still the framework in which we live our lives, make decisions, remember the past, and plan for the future. The flow of time is a genuine part of our experience, even if the ultimate description of reality is timeless. But saying time is emergent does change how we think about it. It suggests that time isn't a fundamental feature of the universe, but a feature of how we interact with the universe. It's dependent on our scale, our perspective, our ignorance of microscopic details. This has philosophical implications. It suggests that the flow of time, the sense that the present moment is special and unique, might be more about us than about the universe. The universe, at its deepest level, might just be a network of events and correlations, with no preferred moment, no global now, no fundamental distinction between past and future. Yet we experience time flowing. We feel the present moment. We remember the past and anticipate the future. Where does this come from? That question brings us from physics into the territory of consciousness and phenomenology, to the study of how we actually experience time. Because even if physics tells us time is emergent or illusory or merely relational, our conscious experience of time is undeniable and immediate. We live in time, through time, as time. Understanding the physics of time is one thing. Understanding how we experience time is another. And the gap between them is one of the deepest mysteries we face. We've journeyed through the physics of time, from the fusion of space and time in Relativity, to the timeless equations of quantum gravity, to theories where time emerges from deeper structures. But there's another crucial perspective we need to consider: how time appears in conscious experience. Because whatever physics tells us about the fundamental nature of time, we undeniably experience it flowing, moment to moment, carrying us from past, through present, into future. This experience of time is so fundamental to consciousness that it's hard to imagine being conscious without it. Even in dreams or altered states, there's still a sequence, a before and after, a sense of temporal flow. The philosopher Edmund Husserl called this the time consciousness, and he devoted considerable effort to understanding how it works. Husserl's analysis begins with a simple observation. When you perceive something that unfolds in time, like a melody, you don't just perceive isolated notes. You perceive the melody as a whole, as a unified temporal object. You hear not just the note playing now, but somehow the notes that just played and the notes about to play. The present moment contains more than just the present. Husserl distinguished three aspects of temporal consciousness. First, there's the primal impression, the immediate awareness of what's happening right now. This is the now of consciousness, the present moment itself. But consciousness doesn't live only in the primal impression. There's also retention, the immediate memory of what just happened. When you hear a melody, you retain the notes that came before, even as new notes sound. This isn't recollection, where you actively remember something from the past. It's more immediate, more present. The just past notes are still somehow there in your consciousness, fading gradually but not yet gone. And there's pretension, an anticipation or expectation of what's about to happen. When you listen to music, you don't just passively receive each note. You anticipate where the melody is going. You expect certain resolutions or continuations. This expectation is part of your present experience. So, the present moment of consciousness isn't a knife-edge instant. It's thick, extended, containing not just the immediate now, but also the recent past, through retention, and the immediate future, through protension. Husserl called this the living present, and it's the temporal structure that makes coherent experience possible. Think about it. If consciousness were truly instantaneous, a sequence of isolated moments with no connection between them, you couldn't perceive a melody. You just hear a disconnected series of notes with no musical meaning. But you do hear melodies, and that means your consciousness spans time, integrating moments into a flowing continuity. William James, the American philosopher and psychologist, called this extended present, the specious present. He noted that we're immediately aware of a duration, typically a few seconds long, over which we can perceive change and flow. This isn't memory, which involves recalling something no longer present. It's direct perception of duration. The specious present seems to last between a few hundred milliseconds and a few seconds, depending on the task and the individual. This is the temporal window over which consciousness directly integrates information. Events within this window feel present, part of the now. Events outside it feel past or future. This has been studied empirically. Neuroscientists have found that perception naturally segments into units of a few seconds. When you listen to a sequence of beats, you spontaneously group them into patterns of 2 to 4 seconds. When you watch ambiguous figures that flip between two interpretations, the flips happen every few seconds. This seems to be a fundamental timescale for conscious processing, but here's something interesting. Our subjective sense of time isn't constant. It varies. When you're frightened or in danger, time can seem to slow down. The famous slow motion effect during accidents or falls has been studied. Interestingly, it seems to be a retrospective effect. At the moment of the frightening event, your time perception isn't actually finer, but afterward, because you are paying intense attention and encoding rich memories, it feels like more time passed. Similarly, time speeds up as we age. Children experience a day as much longer than adults do, a year as an eternity. For older people, years seem to fly by. Part of this might be proportional. A year is a larger fraction of a child's life than an adult's, but it's also about novelty and attention. Children encounter new experiences constantly, each one encoding rich memories. Adults fall into routines, days blending together. Rich, novel experiences make time feel slower in retrospect. Routine makes it feel faster. There's also the phenomenon of being lost in time. When you're deeply absorbed in something, whether work or conversation or flow states in sports or music, time can seem to disappear. Hours pass in what feels like minutes. You lose track of time, not because time stops, but because you stop monitoring it. Your attention is completely engaged with the task, not with the meta-awareness of time passing. And then there's memory, which creates our sense of a personal past. Memory is crucial to our experience of time because it gives us a history, a sequence of events that we can place in order. But memory is also reconstructive and imperfect. We don't record experiences like a video camera. We encode fragments and reconstruct narratives. And this reconstruction happens in the present, colored by our current knowledge and emotions. This means our sense of the past is always created now, always shaped by the present. The past isn't a fixed thing we access. It's something we rebuild each time we remember. And this rebuilding is always happening in the flowing present, always shaped by our current perspective. From a neuroscience perspective, different brain systems seem to handle different aspects of time. Short intervals, milliseconds to seconds, might be processed by the cerebellum and other subcortical structures. Longer intervals, minutes to hours, seem to involve the prefrontal cortex and hippocampus, areas crucial for working memory and attention. But there's no single time center in the brain. Time processing is distributed, emerging from the interaction of many systems. Some researchers propose that time perception arises from the brain's ability to maintain sequences, to track the order of events and the intervals between them. And here's where we come back to physics. The time we experience, this flowing, directional, structured time, doesn't obviously match the time of fundamental physics. Physics, at least in its time-symmetric formulations, doesn't privilege any moment or any direction. Yet we experience a definite now, a definite flow from past to future. Why? One answer, as we discussed with Rovelli's thermal time, is entropy. The second law of thermodynamics gives us an arrow of time, a direction in which things naturally evolve. And our brains, our bodies, our metabolism, all operate in accordance with this arrow. We're thermodynamic systems, far from equilibrium, constantly dissipating energy and increasing entropy. This thermodynamic arrow might be what grounds our psychological arrow. We remember the past because records, memories, traces of the past exist as low entropy structures created by past events. We don't remember the future because the future hasn't created any such structures yet. Causes precede effects because causes are low entropy events that propagate consequences forward in time, increasing entropy. In this view, our experience of time flowing is intimately connected to the thermodynamic structure of the universe and our place within it as entropy-generating beings. We're not passive observers of time. We're participants in the entropic processes that define time's direction. But there's still a mystery here. What philosophers call the hard problem of temporal phenomenology. Even if we understand the neural correlates of time perception, even if we understand how thermodynamics creates an arrow, we still face the question, why is there something it's like to experience time flowing? Why does the present moment feel present? Why do we have this sensation of time passing, of moments succeeding one another? These questions touch on the broader mystery of consciousness itself. Consciousness seems to have an irreducibly temporal character. You can't imagine being conscious without experiencing some form of temporal flow, some succession of thoughts or perceptions or feelings. Even in the most abstract meditative states, there's still a sequence, a before and after. Some philosophers and physicists have speculated about deeper connections between consciousness and time. If time is emergent, arising from quantum entanglement or thermodynamics or coarse graining, might consciousness play a role in that emergence? Is the act of observation, the collapse of the quantum wave function, somehow tied to the creation of time? These are highly speculative ideas, and there's no consensus on them. But they point to deep questions at the intersection of physics, neuroscience, and philosophy. Questions about what time is, where it comes from, and how it relates to our conscious experience. What we can say is this: the time of physics and the time of experience are not obviously the same thing. Physics suggests time might be emergent, relational, or even absent from the fundamental description. Experience tells us time is immediate, flowing, undeniable. Bridging this gap is one of the great challenges facing any complete understanding of reality. Perhaps the resolution is that both perspectives are valid, each in its own domain. At the level of fundamental physics, time might indeed be emergent or illusory. But at the level of thermodynamic, macroscopic systems like brains and bodies, time is real and flows. We inhabit the emergent level. Our consciousness is a macroscopic phenomenon, and for us, time is as real as anything can be. Or perhaps there's a deeper truth waiting to be discovered, a framework that truly unifies the timeless description of physics with the flowing time of experience. We don't know yet. The question remains open. What we do know is that time, however it works at the fundamental level, is central to how we understand ourselves and our place in the universe. It's the dimension in which our lives unfold, in which we make choices and bear their consequences, in which we connect with others and create meaning. Time might be emergent, but our experience of it and the life we live within it is as real as anything we know. We've traveled a long way through the physics and philosophy of time. We've seen how Einstein unified space and time into spacetime, making them inseparable dimensions of a single geometric structure. We've explored how time itself might have begun with the Big Bang, making the question, what came before, incoherent. We've grappled with the problem of time in quantum gravity, where time disappears from the fundamental equations. We've encountered theories where time emerges from timeless foundations, arising from thermodynamics, from entropy, from our incomplete knowledge of the microscopic world. And we've reflected on how we actually experience time, the flowing, directional, structured time of consciousness that seems so different from the time of physics. So, what do we make of all this? Can time exist without space? The answer, as you might expect, is not simple. It depends on what you mean by time and what you mean by exist. If by time you mean the temporal dimension of relativistic spacetime, then no, it cannot exist without space. In general relativity, space and time are unified. They're aspects of a four-dimensional geometric structure, and that structure is what exists. You can't have curvature of time without curvature of space. You can't have the temporal dimension without the spatial dimensions. If by time you mean the flowing, directional time we experience, the time that goes from past through present into future, then the answer is more subtle. This experiential time seems to be connected to thermodynamics, to entropy, to the arrow defined by increasing disorder. And thermodynamics requires systems with many parts, spatial extent, interactions across space. So in this sense too, time seems to need space, or at least, the kind of time we experience needs the kind of spatial structure we inhabit. But if by time you mean whatever plays the role of time in the fundamental description of reality, then the answer becomes murky. Because at the fundamental level, in quantum gravity, there might not be a time variable at all. Time might not exist in the way we think it does. It might be emergent, relational, or a useful approximation that breaks down at the Planck scale. And if time is emergent, if it arises from something more fundamental, then the question shifts. We might ask, what are the conditions necessary for time to emerge? Does emergence require space, or can it happen in other ways? Some theories, like Horjava gravity, suggest that time and space can separate at high energies, that the unification we see in relativity is a low-energy phenomenon. In that view, time and space have independent existences at the most fundamental level, and their merger into space-time is something that happens as the universe cools and expands. Other theories, like those based on quantum entanglement and holography, suggest both space and time are emergent from an even deeper level of description involving quantum information. In that view, asking whether time can exist without space is like asking whether temperature can exist without pressure. Both are macroscopic properties that emerge together from microscopic quantum states. The truth is, we don't know. We don't have a complete, tested theory of quantum gravity. We don't understand how to reconcile quantum mechanics and general relativity in a fully consistent way. We don't know what happens at the Planck scale or what the ultimate constituents of reality are. These are open questions at the frontier of physics. But what we can say is that the relationship between time and space is much stranger and more subtle than our everyday intuition suggests. They're not separate, independent things. They're deeply connected, possibly unified, possibly both emergent from something else. The universe is not a stage on which events unfold in time. It's a four-dimensional structure, or possibly something even more exotic, where time and space are woven together in ways we're still working to understand. And there's something beautiful in that uncertainty. We've made enormous progress, especially in the last century. Einstein's insights transformed our understanding. Quantum mechanics deepened the mystery even as it answered other questions. Modern theories of quantum gravity are pushing further, exploring possibilities our ancestors couldn't have imagined. Yet the mystery remains. Time continues to puzzle us. And perhaps that's appropriate. Time is, after all, the dimension of our existence. It's intimately connected to consciousness, to change, to causality, to memory and anticipation. Understanding time fully might require understanding consciousness fully, understanding what it means to be a subject experiencing reality from the inside. These are not just scientific questions. They're philosophical questions. existential questions. They touch on free will, on the nature of the self, on what it means for something to be real. If the universe at its deepest level is timeless, a static four-dimensional structure or a network of quantum correlations, then what does that mean for our choices, for our lives, for the sense we make of our experiences? Some find this perspective liberating. If the future is, in some sense, already there, already part of the timeless structure of space-time, then perhaps the anxiety we feel about uncertainty is misplaced. Everything that will be already is. From a timeless perspective, our journey through time is just our subjective path through this structure. Others find it troubling. If there's no fundamental flow of time, no becoming, no real difference between past and future, then what does that mean for change, for growth, for the possibility of things being different? But perhaps we're asking the wrong questions. Perhaps the dichotomy between a timeless block universe and a flowing river of time is too simplistic. Perhaps reality is richer and stranger than either picture captures. What if time is like a color? Colors don't exist in the physical world, independent of observers. Light has wavelengths, but red is a perceptual experience created by our visual systems. Yet colors are real for us. They structure our experience, carry information, evoke emotions. In the same way, time might not be fundamental to the universe, but it's fundamental to how we, as conscious beings, interact with the universe. Or what if time is like a horizon? But the horizon isn't a real physical boundary. It's a feature of your perspective, of your position and limitations. Move to a different location, and you have a different horizon. Yet the horizon is real in the sense that it structures what you can see and know. Perhaps time is like that, a horizon of consciousness, real for us, structuring our experience, yet not a fundamental boundary in the universe itself. These are metaphors, of course, not scientific theories, but they point toward a way of thinking that honors both the physics and the experience, both the timeless equations and the flowing now. Here's what we can be confident about. The universe is more wonderful and more strange than common sense suggests. Space and time are not what they seem. They're unified in ways Newton never imagined. They might be emergent in ways Einstein didn't foresee. They're intimately connected to entropy, to quantum mechanics, to the very fabric of reality. And we, as conscious beings, are participants in this cosmic structure. We're not separate from it, observing from outside. We're part of it, patterns of matter and energy that have organized themselves in ways complex enough to wonder about their own nature. The time we experience is real because we're real. The flow we feel is genuine because our consciousness is genuine. The physicist John Wheeler once said that time is nature's way of keeping everything from happening at once. It's a playful remark, but it contains wisdom. Time, whether fundamental or emergent, serves a function. It provides structure, order, sequence. It makes change possible, and change is what allows complexity, life, consciousness to exist. Without time, or without the emergence of time, there would be no evolution, no history, no stories, no music, no growth, no learning, no memories. The universe would be static, frozen, dead. Time, in bringing the possibility of change, brings the possibility of everything we value. So perhaps the question isn't whether time can exist without space, but why time and space exist at all, configured in such a way that beings like us can emerge and wonder about them. Why is there a universe described by mathematics? Why does it have the particular structure it has, with quantum mechanics and relativity and entropy? Why is it comprehensible to minds like ours? These are the deepest questions, and we're nowhere near answering them. But we've made progress. We've learned that time and space are united. We've learned that time might not be fundamental. We've learned that what we experience as the flow of time is connected to thermodynamics and entropy. We've learned that consciousness and time are intertwined in ways we're only beginning to understand. And we've learned to be humble. The universe is under no obligation to match our intuitions. It's stranger than we imagined, and probably stranger than we can imagine. Time might work in ways we haven't thought of yet. Space might be an approximation to something deeper. Reality itself might be fundamentally different from anything in our experience. But we keep exploring, keep questioning, keep pushing the boundaries of understanding. That's what science does. That's what philosophy does. That's what curious minds have always done. And in that exploration, there's beauty. There's the beauty of the ideas themselves, the mathematical elegance of relativity, the strange coherence of quantum mechanics, the deep connections between time and entropy and information. There's the beauty of the questions, even when we don't have answers. Time is a mystery. Space is a mystery. Consciousness is a mystery. But they're mysteries we can explore. Mysteries that yield to careful thought and observation. Mysteries that connect to each other in profound ways. We live in a universe that's comprehensible enough for us to study, but strange enough to remain endlessly fascinating. A universe where simple questions, like whether time can exist without space, lead to journeys through relativity, quantum mechanics, thermodynamics, cosmology, neuroscience, and philosophy. A universe rich enough to support beings who can wonder about it, and generous enough to reveal some of its secrets when we wonder carefully. That's something worth appreciating. Whether time is fundamental or emergent, whether it can exist independently of space or not, we exist in it. Our lives unfold in time. Our choices, our relationships, our experiences, they all happen in this temporal flow. And that makes time precious, whatever its ultimate nature. So, perhaps the best response to the mystery of time isn't to solve it completely, but to hold it gently, to live fully in the moments we have, to appreciate both the wonder of the questions and the beauty of partial understanding, to recognize that we're part of something much larger and stranger than ourselves, yet intimately connected to it through the simple fact of our existence. We've explored one of the deepest questions we can ask. Can time exist without space? We've seen how physics has revealed time and space to be far more interconnected than everyday experience suggests. From Einstein's insight that they merge into a unified spacetime, to Hawking's proposal that time itself began with the universe, to Rovelli's idea that time emerges from entropy and our incomplete knowledge, we've encountered perspectives that challenge our most basic intuitions. The journey has taken us through some of the most beautiful and profound ideas in modern physics. Relativity showed us that time is relative, that simultaneity depends on your frame of reference, that gravity is the curvature of space-time itself. Quantum mechanics revealed tensions in how we think about time, with its timeless equations in quantum gravity and its strange problem of how time relates to measurement. Theories of emergent time suggested that the flow we experience might arise from thermodynamics, from the second law, from the arrow of increasing entropy that gives time its direction. And we've reflected on our own experience, on the phenomenology of time consciousness, on how memory and anticipation create the thick present we inhabit, on why time seems to flow, even if the fundamental equations don't describe flow. We've seen that the time of physics and the time of experience aren't obviously the same, and bridging that gap remains one of the great challenges at the intersection of science and philosophy. What's clear is that time and space are not separate, independent entities, at least not in the way Newton imagined. They're bound together, possibly unified fundamentally, possibly both, emergent from something deeper. The question, can time exist without space, has no simple answer. because time itself is more subtle and complex than the question assumes. But the exploration itself is valuable. In wrestling with these ideas, we've glimpsed something of the strange beauty of the universe. We've seen how mathematical physics can reveal hidden structures, how careful reasoning can illuminate the familiar, how philosophical reflection can deepen scientific understanding, and we've been reminded of how much we don't know. For all our progress, for all the remarkable insights of Einstein and Hawking and Rovelli and countless others, we still don't have a complete theory of quantum gravity. We still don't fully understand how time emerges or what it is at the most fundamental level. We still don't know how consciousness relates to the physical world or why we experience time flowing. These gaps in our knowledge aren't failures. They're invitations. They're opportunities for future discoveries, for new ideas, for deeper understanding. Science advances by asking questions we can't yet answer, by finding the edges of our knowledge and pushing past them. And the questions about time are among the most profound we face. Because time isn't just an abstract concept for physicists to puzzle over. It's the dimension of our lives. It's where we love and lose, where we grow and change, where we create and destroy. Understanding time more deeply is, in a sense, understanding ourselves more deeply. There's ongoing research that might shed light on these questions. Physicists are working on quantum gravity theories, testing them against observations of the early universe in the cosmic microwave background, looking for signals in gravitational waves, exploring the mathematics of black holes and entanglement. Neuroscientists are studying the brain mechanisms underlying time perception, investigating how we construct our sense of temporal flow, examining what happens when time perception breaks down in neurological conditions. Perhaps in the coming decades, we'll have breakthroughs. Perhaps someone will formulate a theory of quantum gravity that's both mathematically consistent and empirically testable. Perhaps we'll understand how time emerges, or discover that it doesn't emerge at all but exists in a way we haven't yet conceived. Perhaps we'll find deep connections between consciousness and fundamental physics that illuminate both. Or perhaps the mystery will deepen. Perhaps we'll discover that reality is even stranger than current theories suggest, that time is just one aspect of a much richer structure we're only beginning to glimpse. The history of physics suggests that each answer reveals new questions. Each solved mystery exposes deeper mysteries. But that's part of the joy of inquiry. We're not trying to eliminate all mystery from the universe. We're trying to understand it more fully, to see more clearly, to appreciate more deeply the incredible cosmic story we're part of. Before we part ways tonight, I want to thank you for joining me on this journey. Exploring these ideas takes effort and concentration. And if you've stayed with me through relativity and quantum mechanics and emergent time and phenomenology, you've engaged with some of the most challenging concepts humans have ever wrestled with. That's worth celebrating. If you've found this exploration meaningful, if it's given you new ways to think about time and space and reality, it helps others find these ideas, helps the algorithm understand that there are people who want to think deeply about the universe. And if you'd like more journeys like this, more explorations of the cosmos and consciousness, and the profound questions we can ask about both, consider subscribing to Cosmovelle. We're building a community of curious minds, people who find beauty in difficult questions and peace in the pursuit of understanding. Your support, whether a like, a subscription, a comment sharing your thoughts, it tells me that this work is valuable, that there's an appetite for content that takes ideas seriously, that doesn't dumb down the complexity but also doesn't lose the wonder. So thank you, truly, for being part of this. As we close, I want to leave you with this thought. Time, whatever it is, at the deepest level, is the medium of your life. The moments you have, the experiences you're gathering, the relationships you're building, They're all unfolding in time. Whether that time is fundamental or emergent, absolute or relative, an illusion or the deepest reality, it's what you have. It's where you exist. And there's something profound in that. The universe has arranged itself in such a way that patterns of matter and energy, incredibly complex patterns that we call human beings, can emerge and wonder about the nature of time itself. We're asking questions about the very framework in which we exist. That's remarkable. So live in your time. Experience it fully. Feel the flow, the succession of moments, the irreversible unfolding from past to future. Remember that each present moment is precious, not despite, but because it's fleeting. The arrow of time, whether fundamental or emergent, points forward, and we move with it. But also step back sometimes and wonder. Look at the night sky and contemplate the vast space-time we inhabit. Think about the Big Bang, 14 billion years ago, when time itself might have begun. Think about the quantum foam at the Planck scale, where time and space might dissolve into something stranger. Think about the mystery of consciousness that allows you to think these thoughts at all. Hold both perspectives. The immediate, flowing, lived experience of time and the cosmic, scientific understanding of time as a dimension of space-time, possibly emergent, possibly unified with space in ways we're still discovering. Both are true. Both are real. And the tension between them is part of what makes being human so fascinating. The question we started with, can time exist without space, remains open in many ways. But in exploring it, we've touched something important. We've seen that reality is far richer than common sense suggests, that the universe operates on principles that challenge our intuitions, that the deepest truths often lie beyond everyday experience. And we've seen that it's worth asking these questions, worth thinking carefully about them, worth holding them in mind as we move through our days. Because in asking about time and space and the nature of reality, we're asking about ourselves, about our place in the cosmos, about the meaning of our existence in this strange, beautiful, mysterious universe. So as you drift off to sleep tonight, perhaps let these ideas settle gently in your mind. Don't strain to solve the mysteries. Just hold them, appreciate them. Let them expand your sense of what's possible. Time and space, unified or separate, fundamental or emergent, are the stage on which your life plays out. And that life, with all its questions and wonders, is happening right now, in this flowing, eternal, mysterious present moment. Thank you for wondering with me. Until next time, may you find both questions and peace, both understanding and mystery, both the flow of time and the timeless beauty of contemplating it. Sweet dreams, fellow travelers. The universe awaits tomorrow.